Okay, so let's get started. Today, we are going to continue talking about this lecture on regression classification with linear models. This is kind of very important component of the course and machine learning in general, because many other things that you will see later would be basically variants of this lecture. So, for example, we extend from linear models to more complex nonlinear models. I started from the idea that we want to talk about, well, we have this machine learning problem, we have this input. And then it goes through some function f, which would be our model or predictor, and produces some output y. And then we have to kind of measure the quality of our prediction y with some targets. So remember, we are in the supervised learning setting, so we know the target. And then the way to measure it is through some notion of loss, which says that how close or similar or different this y and t are. And we will see that depending on the choice of this loss function, or depending on the choice of problem, we have to choose different type of loss functions. So I talked about modular approach, that we have this module that for most of the remainder of the course we are going to follow. We have a model, we select a model, for example, linear model, then we select a loss function depending on whether the problem is regression or classification. We haven't got that yet, but I'm going to talk about it today. And then we may have something called regularizer, and then using all this combination of all these things, using some optimization algorithm, we then find a model that fits data well and generalizes well. And then by mixing and matching these components, we get many different methods. So I started with supervised learning settings. So we have a target t, we have input x, so we have a function f that relates input to output, and then we have a data set of xi's and ti's, and different data points, which we use for training our model. So we start with regression, which is the case that the output values are real valued numbers. So y's or t's belong to R. And then I introduce a linear model, which is essentially linear combination of inputs through some weights W's. So this is the linear model, and then we so I guess some important thing is W and B, the bias, are called the parameters of the model. And then the hope is that our prediction would be close to the targets. So this is what we want to achieve, but we haven't defined what closeness means. So this is kind of just show how linear model looks like in a one-dimensional case, and then two-dimensional case. So in one-dimensional case, it's just line. Two-dimensional is a plane, and in general, d-dimensional, it would be a hyperplane. So then I talked about this data space and weight space, and I think there was a question here, so I tried to kind of discuss it again. So here the idea is that, so data space is essentially the relation between input and output. So this is a one-dimensional input, one-dimensional output, and then, so basically a linear model describes a line in this case. In the weight space is essentially saying that what corresponding weight leads to that specific line. So for example, consider this line, kind of I'm following. This is a flat line, so it's, but its value at 0, at x equal to 0 is going through 1.5. So its bias or intercept is 1.5. So if we look at it in the weight space, so let's see what point it is corresponded with. So if we go to this weight space, we see that there is a point with W equal to 0, which is the slope of the line, and the bias or intercept equal to 1.5.
I guess I'm confused. What's the value in for specified, because for a given fit, you're just going to have a single, it's just going to be a single. You're just going to have a single combination of each of the J weights.
Right. So I guess the comment was that for each line or for each fit, we will have one point in data in the weight space.
Yeah.
And that's true. Yes. So for each of these lines correspond to one of those points in the weight space. So basically this visualization shows that like when we change the points in the weight space, then we are changing our line in the data space. And later we see that, for example, if we do optimization, optimization is essentially a procedure for moving in this weight space so that the fit in the data space would be good.
Okay.
So that's a kind of general idea. Like, for example, this may be red line. I mean, this is a bit ahead of what we're talking now, but
I'm just trying to conceptually understand why are we calling?
Yeah, so it is just showing that there is this kind of duality or correspondence between these two spaces, but nothing super deep at this step.
Right.
So in D dimension, is it correct that, so there's a question here saying that in D dimension, is it correct that each point in the weight space represent a hyperplane? Yes, that's right. So it would be here, this is two-dimensional weight space, so it is line. If it was three-dimensional weight space, it would be a plane, and so on and so forth. So I think it would be, yeah, it would be D minus one dimensional hyperplane. Or yeah. So now, and then I talked about this linear regression. So, no, I mean, we are talking about linear regression. So we decided on the model, which is linear. Now the question is that now we are given a set of data points, say all these blue dots that you see here. We want to fit a line that fits these points well. So we want to find essentially this W such that when W is multiplied by X, so inner product of W and X, and bias is added to it, so it results in Y, it would be close to T for each of those data points. So we see that we have a superscript Y. So for Xi data point I, our prediction Yi should be close to Ti. And I think this was the point that we kind of stopped last time. And now the question is that how do we define the best fits or best line that passing through these points? So any suggestion or idea? Okay, so suggestion here is that try squared error, right?
Yeah.
Okay, so there is a suggestion here on chat, lower error in total. The question is that, so that's true, we want to have a lower error, but how do you define the error? So we can do squared difference. Okay, so there's another suggestion. Okay, so I guess that's good, like squared error as a loss, but then we choose, or as kind of notion of error, and then we minimize that error. So this is a notion of loss. So the way we quantify the quality of the fit would be through something called loss function, L of Y and T. So basically says that how Y and T are close to each other. And then there are different ways that we can define it, but one way that is meaningful in the context of regression is through squared error loss, which is defined as the difference between Y and T, error in prediction, and to the power of 2 squared. So this is squared error. Y minus T is called residual error or something like that. I mean, there are different people call it different things in different contexts. So here we call it residual. And then we want to make its magnitude of the residual small. And the way that we measure the magnitude is through taking the squared value of it. So the factor of half here is just for kind of mathematical convenience. So making later derivations a little bit simpler, it doesn't really matter. So half, you can have it half or not. Okay, so that was for 1 point. So it says that for 1y and yt, 1t, how different they are. And that's a loss for that point. So now we want to talk about loss over all data points, like we have n data points, so what would be the loss? And here we have the notion of cost function, which would be the loss function average over all training examples. So we define J of W and B. So J now is a function of those parameters of the model, which would be the summation of loss of between Yi and Ti. Okay, so loss here, the choice of loss here was squared error loss. So this leads to the second equation, which would be Yi minus Ti squared. And now remember that, okay, so what for the linear model, what is the relation of Y and parameters and X? It's a linear relation, right? So essentially what we have is that this term is equal to our Yi. So W transpose Xi plus B is the prediction provided by the model at point Xi. And that prediction is, of course, function of W, right? So if we change, and W and B here. So if we change the weights, the parameters, the prediction would be different. And I guess that's the whole point of what we want to do is find those weights or parameters such that this cost function would be minimized. So how do we do it? Well, as just I said, we find the weights that minimize the error. Minimize the cost. So to find the best fit, we find a model which is parameterized by its weights W and B that minimizes the cost function. So we find that minimize of this cost, which is essentially what I wrote here. Is it clear? Okay. So I should kind of warn you that this terminology is not universal, like the choice of what is loss and what is cost function. Different people may use different things slightly. So for example, some people might call what we call loss, which is only for error or loss for one single point. They may call it just point-wise loss. So they use adjective point-wise to emphasize that's for point. And then the cost function, they call it again loss, but they call it empirical loss or average loss. So if you see these things, you shouldn't be surprised. Okay, any questions so far? So there's a question here, which is, do we really need 1 over n? And that's a good question. And the answer is that no, because if we have a minimizer here, the minimizer of, maybe use a different color. This term, with or without 1 over n is the same. Because 1 over n is just like a constant multiply, so it doesn't change the minimizer. So we don't need that. Here I just wrote it to be kind of consistent with how we derived it, but actually you will see that sometimes, I think in a few slides, I mentioned that we can have it without 1 over n, and then we get similar formula for the solution. Okay, so one other thing that is kind of important and you see often in machine learning is that we use vector notation to represent things. We try to use matrices and vectors to simplify our equations. So what we can do, for example, here is that we can organize all training examples into a matrix X, which is called design matrix. And the way we organize it, one way to organize it is we put 1 row per data training example. So how does it look like? So if we have X1 here, so we put it as this row. X2 would be the second row, and X3 would be So we have 3 data points. Each of them are 4-dimensional. So we get a matrix which is 3 by 4. And then we can also put the we can also put the target values in the same way. So if we have target values, here we will have 3 points. So we have 3 targets. Say, so it would be T1, T2, and T3. So it would be 3 by 1 matrix or vector. So the result would be, we can write the whole model, the prediction. So for all data points, like here 3 data points that we have, we can write it multiplication of x times w plus b multiplied by vector of 1. So which looks like this. So this would be 3 by, say, 4 in our case. No, and the result, this would be 3 by 4. The result would be 3 by 1, which is our prediction y. Okay, so this is just a kind of simplified notation. So if we do this, so y, as I had in previous slide, we can write it as y equal to x design matrix times weights plus b. And then we can write the error, the squared error, as a norm in of the vector of the difference between y and t. So, okay, so maybe just a question. So if this is, what's the dimension of, just make sure that we're on the same page. What's the dimension of y if you have n data points? So it would be n by 1, or it would be vector n vector. The same for t. And then, so this would be a norm defined in Rn, right? So this is a norm. Say I write it for u. This is a squared. This is L2 norm, which I think we had a review in the first tutorial. It would be essentially summation of ui to the power of 2. And the dimension is n. And u, of course, here is. So here, instead of u, we have y minus t. Okay, is it clear? Okay, we have some answer here. Okay, yes, that's right. So n by 1. So note that sometimes we have, I think this was a question like 2 minutes ago, that instead of having 1 over n, we just have it without 1 over n. That would be essentially corresponding to sum of the losses instead of the average of them, but it doesn't matter as the minimizer does not depend on n. So this is, I guess, one thing to know. The other thing to know is that we can also add some column of 1s to the design matrix and then combine the bias and the weights into one kind of matrix. So essentially we add a matrix, a column of 1s, and then for the rest of it, each of these xi's would be like a row vector. And then if we do this, we get a design matrix, which is n by d plus 1. And then if we do that, then we can put the bias term, b term, inside the weights vector, and just consider as yet another weight. So that would be b. And then we have the rest of the weights. And then the whole thing would be d plus 1 dimensional vector. And this makes the formula, all formulas much easier, because then our predictions we can write it as x times w. So in most of the rest of the lecture and course, we consider that the design matrix incorporates such a column vector of 1s, so that we don't need to explicitly talk about bias. Okay, so let's go back to where we started. So we want to find a good function f, which when input x goes through this function f, and generates y, it would be close to the target. So we defined a model. So we decided on the model to be linear. We decided on the loss function to be squared error loss. And now the only thing that is remaining to be done is that minimizing this optimization problem that I had a few slides ago. So how can we do it? So let's talk about it a little bit and give some ideas. Like if you are given this optimization problem, so this optimization problem, and then you know that the loss function has this correspondence. You want to find weights, W and B, or maybe we put all of them together into one parameter W. How do we find the minimum?
So it's differentiated. So that's why we have the 1/2 in the beginning. So we can just put the derivatives there, maybe equals to 0.
Okay, yes, that's it. Okay, so yes, so basically the suggestion was to take the derivative of the loss function or the cost with respect to the weight and make it equal to 0. So, and that's a true one. Another suggestion is that by taking the gradients. Okay, so by taking the gradients, and then what do we do with gradients? One way to make it equal to 0 and then solve for it. The other is doing some other iterative procedure. And okay, so like gradient descent. So another suggestion here is that one basic approach, try changing the weights by a small amount and keep changes if loss decreases. Okay, so that's good, except that how do you change the weights, like randomly or not? The truth is that one approach is to change the weights, but in a very specific way, and that would be the gradient descent. I'm going to talk about it in hopefully today. But for this particular problem, we have a solution that is much simpler, maybe. More, yeah. Okay, so you all had your calculus. So minimum of differentiable function, if it exists, it occurs at a critical point, which is the point that the derivative is 0. And if the function is like in the multivariate generalization, we take the partial derivatives and make them equal to 0. So, or equivalently make the gradient equal to 0. So now the task is to find a point that the gradient is very close to 0 or very close to 0. And then sometimes it is possible to do it, find that solution in an analytical way, and we call it a direct solution. And sometimes we can't do it, and we have to use an optimization technique to do it numerically and iteratively. And we will get back to that later. But just let's go through this derivative. I'm not going through the definition of what partial derivative is, but if you want, take a look at it. Basically, we say that we change one variable a little bit and see how much function is changing, and then make the change going to epsilon small, and that would be the partial derivative with respect to it. But I guess the point here is that, so for example, we can do some calculations on our lean model cost function. Yes, there's a question. So the comments, the question is that in this case it is invertible, so maybe we can solve it as a linear system of equation. So that's true, and actually we are getting to that point. But what is actually invertible? Like you need to get to some linear system of equations first, and then invert some matrices as we see. But how do you get to that linear system of equation? Okay, right, but yeah, okay, so I mean, the problem is, well, I guess there are two answers for that. We get to something very similar to this. So, but, so the comment was that we have a design matrix. So let's see, which is n by d, right? Which is d by 1. That's our predictions, essentially. And we wanted to make it equal to d by n by 1, right? And then I guess your suggestion is just take the inverse of x. Right, so we can take a pseudo inverse or something like that. But you will see that, I guess one issue is that how is it related to our choice of cost function that we have selected, right? We said that we want to minimize the square error loss. If we do this inversion or do pseudo inverse of it, is it corresponding to that or not? And we see that, yes, it corresponds to that. But we are going to kind of actually derive it and see that minimizing that squared error loss would correspond to taking some pseudo inverse. Yes.
Don't you already get the equation, the moment that is the total derivative of the cost function? So the already gets like x times weight plus y is equal to y or equal to 0.
So yes, I mean, as soon as you take the derivative of it, you get something like this, and then we can solve it. Yes. So, but I just want to go through the computation of that. Sorry, I forgot to repeat it. The question is that don't we get this the same equation that we have here if we take the gradient, take the derivative and make gradient equal to 0. Okay, so in interest of time, I go through this even a bit faster. So we can compute that for linear model, which can be written in this way. If we compute the partial derivative of y with respect to some weight, we get xj, and it is easy to say that it's kind of linearity of derivation, the differentiation operator. So how do we do it? So also now we want to take the derivative or partial derivative of cost function with respect to weight. So we can use the weight, we can use the chain rule. So the partial derivative of cost with respect to wj would be partial derivative of loss with respect to one specific y, and then partial derivative of y with respect to wj. So this is the chain rule. So what's loss? So for 1 point, it would be half of y minus t squared. We take derivative with respect to y. And then what is the partial derivative of y with respect to xj? It would, wj, it would be xj, because that's a linear equation. So this one, the first term gets to y minus t times x, and then the second term would be xj. So this would be the partial derivative of L with respect to one of the parameters. So this is what's for the loss, for pointwise loss. If we go on average loss or cost, which is average overall training points, so would our j, derivative of j with respect to wj would be summation, or 1 over n of summation of yi ti times xji. I is the index for data, j is the index for the dimension that we are taking derivative. So now, as many of you have already kind of alluded to it, how we do it is that to find the solution, in the direct solution is that we find a point that the gradient becomes 0. So minimum must occur at the point where the partial derivatives are 0. I mean, we have other things. It could be maximum, but we can verify that the function is convex. So its minimum, its critical points would correspond to the minimum. So that's easy to verify. So we compute the gradients of cost function with respect to weights w and equate it to 0, which means that if we want to write in a more expanded form, it would be the partial derivative of j with respect to all weights j, for all j's, that should be equal to 0, and the same for the bias term. And the intuition is that if this wasn't equal to 0, so it means that there is a direction that we can change W's a little bit, and if we go in that direction, the cost function would increase or decrease. So if we go in the direction of opposite of the partial derivative, the cost function would decrease, and that means that there is a room for having a better solution. As we will see later, this is a basis of a method called gradient descent. But here, in this case, we don't need to do that. We can compute this, equate this gradient to equal to 0 and solve it using linear algebraic techniques. So if we follow this recipe, we get that we have to set the gradient of this cost function equal to 0. So what is y? Y is equal to x times w. So just repeating what we had before. So, and bias is absorbing x. So the gradient or the cost function can be written in matrix form or vector form as xw minus t transpose times xw minus t. We can change it, check that the dimension is correct. So recall that x step, that was n by d. This was d by 1. So xw would be n by 1. So this term would be n by 1, but transpose. So it would be 1 by n. This would be n by 1. So the whole multiplication would be n by 1, scalar as we want. It's a number. It should be a number. I mean, if we did it the other way around, we would get n by n matrix, which wasn't what we want. So that's a kind of easy way to check if you are doing these things correctly. So we compute the gradient. So what would the gradient? Gradient would be 1 over n x transpose xw minus t transpose. This should be equal to 0. So again, I guess we expand it. We have x transpose x times w is equal to x transpose t. So you see that this is a linear system of equations. So we want to find this w. We know the right-hand side, we know the left-hand side. So these are basically we can construct all of it using data that we are given. So this is, oops. So x's is essentially just depends on inputs. This is the targets that is given us in the supervised learning context as a part of the training set. We solve this, and if we assume that this x transpose x is an invertible matrix, then we get that the weight that minimizes the squared error loss is x transpose x inverse times x transpose times t. Right? Sure.
So what after the derivative, why it's x transpose and
so this is actually interesting. This is basically essentially rules of how if you take derivatives of matrices or vectors, what the order should be. And there are different conventions, but the way you can check it is that the dimensions should be correct. What is the dimension? Okay, so maybe check it. Give you an idea why this is actually the right dimension. So what is the dimension of gradients? So, okay, so sorry, the question, I forgot that I should mention, repeat it. So the question is that why we have x transpose here instead of x, for example, right? So what is the dimension of gradient of j with respect to t? It should be n by 1 or d by 1. It's a gradient, so grade, remember, so the answer, one answer was that n by 1 here on the chat. Remember that we have weights are d-dimensional. So maybe I'll write it. So x's belongs to n-dimensional space. Weights belong to d-dimensional space. I guess in previous slides I used capital D, but doesn't matter. So we take some function that compute the derivative of it with respect to each of those weights. How many of those weights do we have? D. So this should be d-dimensional vector, or d by 1. And then let's check. So x, we had it, x was n by d, right? From previous slides, x, the way that we put it is that we put one data point in each row. So x transpose would be, maybe just, so this would be d by n. Okay, so this would be, I think that transpose is extra. So this would be n by d, d by 1. So the whole thing would be n by 1. So we have d by 1 matrix here, multiplied by d by 1, so n by 1, so that the whole thing would be d by 1, which is the dimension that we want. So that kind of remember, this was there was a transpose here that should be was extra. But other than that, the first x was x transpose. So this is just checking the dimension, if that dimensions are correct. There are different conventions how to do derivative with respect for vectors and matrices. And there's no one single standard, but if you just follow them consistently, you should get the correct result. So there is something called matrix cookbook if you want to check. That gives you a kind of a nice kind of manual or guideline how to do it. So if you search matrix cookbook, you find it. But the test is that check the dimensions to see if the dimensions are what we expect or not. So actually, speaking of checking dimensions, so what are the dimensions of each of these components here? So what's the dimension of x transpose x? Right, yes, so it's d by d, so we take inverse of it. And then x transpose would be d by n, and this would be n by 1. So you see that we have d by d multiplied by d by n, so it would be d by n multiplied by d by n by 1, so it would be d by 1, which is consistent with the dimension of our vector weights being dimensional. Okay, so there is a, right, so in real so there's a question here, in a real implementation of linear regression, do we check if x transpose x is invertible at the beginning? Sounds like gradient descent is a safer choice in general. So that's actually a good point. In practice, what might happen is that that matrix would not be invertible. Maybe it would be rank deficient, or it might not be rank deficient, but it would have a very bad condition number, which basically means that the largest eigenvalue versus smallest eigenvalue, the ratio of them is very large, which makes the errors, make the numerical errors very large. Also from a statistical perspective, and we will see it soon, somewhat, not in very detail, but as I mentioned. If this condition number is not very good, then the performance, statistical performance, like generalization ability, would not be very good. So what we do is that in practice, if we wanted to go through this direct approach, we add some regularization coefficient to this matrix. So we change this matrix to something like x transpose x plus lambda I. I is the identity matrix, and lambda is a positive number. And then we take derivative of it. And this makes sure the system would become first full rank, and then it improves the condition. Yeah. right? So I guess another thing is that comment here is that B is absorbed in X. So XT should be dy B plus 1 times F. That's right. So that's kind of partially the reason I use D, small letter D instead of capital letter, just to avoid writing extra thing with D being, small letter D being capital letter D plus 1. Okay. Okay, so let's, so far we talked about linear models, but in practice, many data points that we observe are not going to be linear, right? So for example, the relation between input and output is not going to be linear. So if we have these data points, these blue ones here, you see that it follows this curve. So we can't fit a very good linear model to it. But the kind of the beauty of this linear regression is that we can still use this linear regression framework by mapping the input values, x's, to another space, to something that is called basis expansion or feature mapping. So essentially, and you see how we do it. But essentially, we choose some function psi that takes input x, which is RD, and maps it to some other space, R small letter d. And then treats now, so that small letter, so this is kind of, can be some processing on inputs. It can be a nonlinear map in general. And then we treat the mapped features, which is in R small letter d, as input of a linear regression procedure. So we have some initial input space. So in the weight space, in data space. So we have RD, we do some processes on it, and we get on our capital small letter d. For example, D here might be 1, D here might be 5. So we kind of expand the dimension, and that's why we call it basis expansion. So let's see how it works when input is one-dimensional. And for this size, we use polynomial features. So what does it mean? It means that we choose to be a mapping that takes changes x to constant 1, x squared, x to the power of 3, and so on and so forth. So different powers of x. So if we do this choice, the linear model that we have would essentially be like this. So we will have W0 plus W1x, W2 x squared to Wm times x to the power of n, which can be written again like this. So note that this model is not linear in x's anymore. So x's are into power of I. So this is not linear in x. But the model is still linear in weights. So you see that the weights are essentially, we multiply each weight by some constant, or not some constant, something that's a function of x, but the relation of these things is still linear. So we can still use the same framework of linear regression as before, but just instead of considering our model to be x transpose x, we consider our model to be psi transpose W. Sorry, I guess before I said, so instead of having model to be W transpose X, or maybe make it consistent here, X transpose W, we change it to psi of X transpose W. So in general, phi can be any function. For example, another example would be take the Fourier expansion. So we say psi of x psi of x would be equal to 1 sine of 2 pi x cosine of 2 pi x sine of 4 pi x cosine of 4 pi x and all the expansion of Fourier basis. So this is the idea. So I get back to this soon, but just I come back to this in a minute, but just see how it looks like if we do this fitting. So if we choose our model to, like this model that we have here, and choose different values of m, which means that different order of expansions or degrees of expansion of this polynomial. If we choose m equal to 0, the model would be essentially y is equal to w0. So the best fit for this data would be this red line, which is a flat line. So it doesn't have any slope. It is just has a bias. So this is not a very good fit. If we add another dimension to that expansion, so have m equal to 1, so our model would be w0 plus w1x. We see that we get a linear fit, which is much better, but it is not great. If we increase the order of expansion, so we include x squared and x cubed, we see that we get a pretty well fit to the data. And if we do this again with up to the power of x to the power of 9, we see something interesting. So the fit is very good, actually. Like it passes through all data points that we have. But it doesn't look very good if we consider that the underlying true function, which we don't know, we only have noisy sample from it, is this green curve. So you see that there's a lot of jumps at these points. So this is a very good fit to training data points. So it passes all the data points, but probably we don't consider it as a very good solution for this regression problem. Okay, so what has happened? Answer was overfitting. So what does overfitting mean?
It fits the fast data and only the fast data.
Can you repeat again?
It fits the fasting data and only the fasting data for training data.
So it fits the training data, right? So the answer is that it fits training data, but only training data, but it doesn't essentially generalize to test data. So yes, okay, so another comment is that similar to doing a KNN with k equal to 1. And another answer is that you have a model perfectly fitting training data, but then not validation data or test data.
And from a model that's higher order, like significantly higher order than the actual problem.
Right, so the answer here is that it is significantly higher order than the actual order of the problem or model that generated the data.
Yeah. And that's always going to happen, right? When you have an M that is equal to at least the number of points times 1.
Right, so if we have
Here you have 10 points and it's just 9.
so that's a good point. So comment is that if you have, if the order of your model is lower than the number of data, is higher than the number of data points that you have, this always would happen. Like if you have more degrees of freedom, you would overfit to data points. So these are all good. So let's just, we talked about overfitting and underfitting in the first lecture, but let's talk about it in this context. So when m was equal to 1, we have underfitting. Model is too simple and it does not fit the data well. Overfitting is that model is too complex. It fits the training data perfectly, but it doesn't generalize well. And if we actually compute this, compute the error as a function of order or complexity of the model, as a function of m. So this is similar to what we had before in the KNN case, that we change the k and see how was the training error was changing and how was testing error or validation errors changing. And if you recall, when k equal to was 1, training error was 0 because we fit every data point fail, but it is not necessarily the best testing error. So we have something, now M is our hyperparameter. So we see that when M, so here blue is training, red is testing. So you see that when we increase the model, the training error starts decreasing, and at some point, it becomes exactly equal to 0. But then the testing error, in this case, it starts decreasing, but at some point it becomes kind of plateaus, and then it goes, oops. I think we, okay, that's good. But then it starts increasing. And you see at the points when M is 9, it is not actually performing well at all. Some point in between, like when M is equal to 3, 4, the performance is, training error is relatively small, it's not 0, but also its performance on test data would be also good. So just a question, how do we find a good M? If I give you a bunch of data points, how do you find it? Yeah. Sorry. Generate plot like that, yes. So, but how do we do it? We don't, if you want to tune it, you don't tune it usually using test data, right? Validation. So yes, so exactly. We generate the plot like this or compute a plot like this, but instead of testing data, we choose M based on the validation set. So, okay, so here I guess, let me see, there are some questions. Is there a way to formulate overfitting? Is training error minus validation error good enough? I mean, there are ways, I guess, to formalize it mathematically. But here, I guess, I'm not going to give a very formal definition. Essentially, yes, if training error is smaller than validation error, we have an overfitting. Okay, iterative different point until. So I guess this is that iterate different points, like I think M, until validation error converging or before going higher again. So, okay, different M's, right? So I guess that's the thing, like we compute it until we essentially find the minimum of the validation set, but we know how to do it. So let's look at another thing here. If we fit the model and look at the weights that the fit has. So if the W for M equal to 1, we have 1 weight and it would be 0.19. If we have model M equal to 1, a linear model, which is like W0 plus W1 times X, you see we have these 2 weights, these 4 weights for M equal to 3. And if we see M equal to 9, we see we get these 10 weights. So what is noticeable in the weights of the case of M equal to 9 versus the previous cases?
Absolutely.
So yes, exactly. Like they become very large. Right? This is, I don't know how big it is, but order of millions. So the weights becomes very large. So essentially what the method is doing is that finding a coefficient that finds close or matches data very closely, but then the result would be the weights can become very large. What is, I mean, one intuitive way to think about it, of the effect of having a large weight is that small change in our X leads to a big change in our prediction. So if I have a coefficient, for example, this is, like consider this term, which is, I don't know, I guess the 1 million, order of million. So if you have a 1 million times X to the power of, I think, 6, for example. And 6 is just, both of them are 6 by coincidence. So if we fit the training data, it finds these weights so precisely that the training error would be 0. But if I change x to x plus epsilon, like I move from this point, I want to show it on this figure. If at this point, I have a best fit. But if I move a little bit from x to x plus epsilon, what I'm effectively having is x plus epsilon to the power of 6 times 10 to the power of 6 again. And this is effectively, I mean, we can expand it again, but we have a term which is 10 to the power of 6 times some function of epsilon. So it would be x to the power of 6 plus other terms that we have. Even though epsilon might be small, like 0.1, when we multiply it by a very, very large number, like 10 to the power of 6 or 7, the effect would be very large. So this shows that our prediction is not going to be stable. Small change in the input would lead to a large change in the output. And that's why we see observation like this, that on the training set, we have a very good fit, but the model has a lot of oscillation between those training sets, training points. So what does this suggest? I'm going to talk about soon, but like if you have a problem, if you think the source of problem is that the weights becomes too large, can you think of a way to prevent that? And as a result, avoid this oscillatory behavior, which leads to having the bad generalization capability of the model?
You can consider concept of cost function for reduce the weight.
Okay, so we do something to the loss function to reduce the weight. So what can we do for doing that? Oh. So another suggestion was to add sum of square of weights to the loss function. So that's great. So that's the correct answer. And also we have here that using regularizer, which I haven't defined yet, but that's correct. That's called regularizer or penalizer. The other is that, okay, regularizer penalizes large magnitude of W's. Or another suggestion, which is also good and related, is that using some constraints on weights. So we make sure that the weights do not get larger than magnitude of 5, for example. If we do that, then we are effectively in the weight space. We are saying that you can't go everywhere. You have to just stay close to certain weights, like small weights. And these are all good. And that's the idea of regularization. Okay, so maybe I just talk about this figure, and then we will have a break soon after. So usually we have this kind of behavior that we have, we see some figures like this in machine learning, which basically describes the effect of training data that we have on the error. And also some figures like this that shows that the effect of number of parameters that we have on the error. So usually what we have is that, okay, if we increase the number of training examples, and this is error, so different errors, in the beginning, training error can be very small. But then as we increase the training examples, you generally see kind of increase of training error. And then, but if you look at the test error or validation error, you see that in the beginning, the validation error is large, but as you have more data points, your test error starts to decrease. And kind of eventually, if the model is good enough, the gap between training error and test error should go to small values if the model has some consistency property. So a question is, so basically what is happening here is that if we have more data, we can be more confident about the estimation of our parameters. Or maybe I should say it this way. So so maybe answer this question. Why here when training error is small, or training examples is only a few, training error is small? Yes?
So, as the number of training samples increasing, you said the training error is increased. Are you talking about the average training error or the total?
What's the average? What is total? Oh, right. Yes, average.
So why the average training error is increasing?
Yeah, that's the question. Like, why in the beginning? Like, suppose I give you 2 data points, and suppose your model is one of those polynomial models. Suppose I choose m equal to 5. The model is fixed, and number of data points is 1. What would be the training error in that case? 0. Why?
Because of overfitting?
Right, exactly. So the reason is that if n is small compared to the complexity of the model, and in this case, complexity is like the degree of the polynomial. If you have m equal to 5, n number of data points equal to 1, we have a perfect fit. If you have n equal to 2 or 3 or 4 or 5, in general, we have perfect fit. So in the first training examples, the training error would be 0. And then it gradually starts increasing. But
Is
yes.
it because of overfitting?
The difference between 1,000 samples and 2,000 or 10,000 samples. We never train the 5 parameters with like 1 or 2 samples. But how do you explain it with like 1,000 samples compared to 10,000 samples?
Right. So this is kind of rough. So I guess the comment or question was that this example that I gave is extreme case because I have 5 data points, and then my model is also very simple, have 5 parameters. So, but what if the number of data points is 1,000? So what happens in that case? So that's true. So this is kind of like a rough estimate of what behavior you might expect, but also you need to consider that some models can be actually very complex, like a neural network might have millions of parameters. So in the regime that you only have thousands of data points, you are still in the regime that the number of parameters is higher than the number of data points that you have.
Yeah, but I think in reality, the number of data is always larger than the number of parameters. Otherwise, you can't get the model.
So that's a good. So I guess it depends. Like in many, like in some models, that's okay. So the comment was that in reality, the number of parameters is always smaller than the number of data points. And the answer is that it depends. Actually, for neural network, this is not the case that people use. But in many simple models, like the fact we may see, like in this lecture, or in many small data sets, that's what you're saying is true. But in, say, neural networks, we have billions of parameters and millions of data points. So actually, we are in the over-parameterized case.
I think of it more as just like the more samples you have, like your model's some parts of what you're really trying to represent.
Mm-hmm.
And the more samples you have, the more opportunity there is for like higher order noise and stuff that your model doesn't capture to drive that. Basically to drive that error.
So the answer is that if I can summarize it, saying that when you have smaller number of samples, you have more opportunity for the model to kind of capture stuff.
Whereas as you start to get more samples, it's more likely that you're going to get some weird noise that
right.
your model just doesn't capture.
Yeah. So okay, maybe I should say like this. These figures are approximate what's happening. The detail of it depends on the specifics of the model. But the general idea is that when you have more training data points, your testing error starts decreasing. And in the regime that your models relatively have more parameters or some form of parameters, some sense of complexity than the number of training points, you are starting in the overfitting. You're overfitting to the data points, but as you increase the number of data points, overfitting goes away. And in overfitting, you have smaller values of the cost. So as long as you're overfitting, this training error would be small. When you are not overfitting anymore, training error is not going to be kind of extremely small. So we have kind of growing behavior. For training error, we have a decreasing behavior for test error. So this is as the number of training examples. But on the other hand, when we change the parameters or complexity of the model, we see a different behavior. As we increase the number of parameters, but we fix the number of data points. So we observe that for training error, in the beginning, when the number of parameters is very small, we don't have a very good fit. So even we can make the training error to go to 0. But as we increase the number of parameters, we have a better and better fit. And at some point, the training error might become very close to 0 or become very small. In the example that we had, it can become exactly 0. In some cases, it won't become exactly 0, but it becomes very small. But on the other hand, if we look at the test error, we see a kind of a U-shaped behavior. That in the beginning, when the number of parameters is very small, the method is not having a very, we can't essentially perform a good prediction of the values for a new point because the data doesn't look linear, but we are in a linear, we are using a linear model. So test error is also large. And then we get at some point, which it gets a minimum, but after a while, when parameters becomes larger and larger, and remember the data points are still fixed, test error, we start having overfitting and test error increases as well. Okay, so maybe we have a quick break here. So it's 18 past 12. Maybe we start at 22 for 4 minutes. Okay, so what we want to do is that introduce the concept of regularization, which is a way for controlling the model complexity. So here in this example that I had, M was the degree of the polynomial, and that controlled the complexity of the model. So M would be a hyperparameter, and we can set it, as you mentioned, using validation set. So that's all easy. But now you can argue that the restricted number of parameters of a model is just a crude approach to control the complexity of the model. But a question is that maybe we want to have a better approach to controlling the complexity, which is not just going through a set of integer numbers of m equal to 2, 3, 4, 5. So the idea here is that we actually choose a relatively large m, but somehow enforce simpler solutions. So here we keep the number of parameters of the model large, but enforce simpler solution in some way. And this is done through something that is called regularization or penalization, which is essentially saying that certain solutions are preferred compared to the other solutions. Something happens here. So essentially it is saying that we can interpret what regularizer is doing, and I'm going to talk about it, what actual regularizer looks like. But the idea is that it's a function that quantifies how much we prefer one hypothesis or one set of weight parameters. So I'm using hypothesis equivalent to the model or equivalent to the parameters described in the model So how much we prefer one of them versus another before seeing the data. So we haven't seen the data, but we say that we prefer to have smaller weights instead of, we don't want to see a weight or in the order of 10 to the power of 6. We prefer to see something that order of 10, for example. If you have that preference, that's before seeing the data. Maybe data pushes you to have large weights. But if it doesn't, but before saying that, we say that this is our preference. And that preference is encoded using this penalizer or regularizer. The question is, of course, how to have this characterized or how to make it happen. And one idea is that we encourage weights to be small. So our preference would be to have smaller weights, by choosing as L2 norm as our penalty. So we say that our regularizer is a function of W's, which is taking the L2 norm squared of weights, which can also be expanded as like summation over all weights of Wj to the power of 2. And J is d-dimensional, so it is d-dimensional summation. So here we are penalizing the squared L2 norm. So that's one regularizer. And then we add this regularizer to our penalty, or to our cost function. So this is the cost function that we had. So it was the average or sum of squared errors. And then we add lambda times our regularizer. So in this case, that we have L2 norm. For regularizer, we get JW plus lambda, half of lambda, summation of Wj to the power of 2. So the basic idea here is that simpler functions have smaller L2 norms of the weights, and we prefer them to functions with larger L2 norms. This is one definition of what simpler looks like. I think from the polynomial case, you can see that functions that have large weights might have showing oscillatory behavior. So effectively, we are saying that in that case, we don't want to have those oscillatory behavior. Okay, so that's the idea of regularizer. So just maybe kind of, we try to kind of study it a little bit, how it behaves. So suppose we have a fit to data. So it means that some specific choice of W's. But the fit has the training data, or those weights do not fit the training data very well, which means that our cost would be large. Like J, the average of the loss functions would be large. So that's one thing. So we know that a fit that is not very good to data has a large cost function. But on the other hand, if the fitted weights have large values, R would be large. Now, if we choose a larger lambda, there's regularizer coefficient here, we are saying that we want to penalize or pay more attention to the size of the weights. So we penalize weight values more. If we choose lambda to be very small, we are saying that we don't care much about the choice of the size of the weights. And effectively, we want to only mostly focus on how well the model fits the data. So lambda would become a hyperparameter that we can tune with the validation sets. Okay, so for the least square problem, so we had this J as before. So it would be L2 norm of XW minus T. And then if we have a regularizer, then the regularized cost would be this term. So it would be, this is the fit error from fitting. So this is the cost. And this is the term from regularizer, L2 norm squared of W's multiplied by lambda. And this whole thing becomes regularized cost. And if we solve it, we solve the minimum of it, we get something like X transpose X plus lambda n I n times n number of data points. I is identity matrix, the whole thing square inverted times X transpose T, the target values. So you see that the difference from the previous case, from least square case solution that we got, is that there we didn't have lambda, so it was equal to the case that lambda was 0. So if there was no regularizer, in that case, it reduces to least square solution. Okay, question: what happens when lambda becomes very, very large, like goes to infinity, for example? Okay, so the answer is that all weights goes to 0, and that's true. So if lambda goes to infinity, essentially this second term becomes the dominant term in optimization problem, and the effect of the first term would become small. So the optimizer tries to essentially pay attention to L2 norm of W. The minimum for L2 norm of W is when weights are all equal to 0, right? So if we have a minimization problem, which is just this, the solution of it would be weight equal to 0, right? That's a minimum norm of weights. So if lambda becomes much smaller than, much larger, very large number, it dominates the first term, which is the cost function. On the other hand, if it is 0, essentially we don't have any preference for smaller values. And then between these two extremes, we have a trade-off between these two cases. Okay, any question about regularizer so far? Right, okay, so there's an answer here. The optimizer always prefers extremely small W. So there is a question, why are we dividing by 2 over n? If you recall, the cost function was defined as the average loss. So that n, 1 over n comes from there. But also, as I mentioned here, is that sometimes instead of having 1 over n in the formulation, we have without 1 over n. And then if in that case, the solution that we get would be X transpose X plus lambda n, so without any n. And both of them are common in literature, so it doesn't really matter. The only thing is that what coefficient we are using. Okay, any other question? Is it clear how? Yeah, perfect. Okay, so L2 norm, or squared value of L2 norm, is one choice of regularizer. Another choice of regularizer is L1 norm, right? Which is essentially, we say that we take L1 norm of W, which is just the sum of absolute value of weights. And if we do this in the context of regression, we get a method called least absolute shrinkage and selection operator, or lasso. I mean, the name doesn't basically say much about what the algorithm is, but I think it's enough to know that it's called lasso, which is the same as previous case, but instead of L2 norm, we have L2 norm squared, we have L1. I think I forgot to mention that this method, what we have on this page, it's called ridge regression. So that's a kind of the name that is called. Ridge regression is when we have least square error plus L2 norm for the regularizer. If we change L2 norm to L1 norm, we get so-called lasso. And it can be shown that lasso encourages weights to be exactly 0. Not, of course, always, but it pushes weights to be 0, and in some cases, they become exactly 0, not like 0.001, but exactly 0. I try to give you a kind of intuition why it is the case, but it is not going to be a formal truth. So you need to believe something from me that this is what is happening. Okay, so I try to give you I think well, half an hour ago, I talked about how we can penalize weights. One idea was that, or make sure the model doesn't overfit. One idea was that to constrain the weights to be within some region. So we say that we don't want weights to be outside as magnitude larger than 10. The way that I define regularizer wasn't saying exactly like that. It was in the form of penalty. I add this penalty as a regularizer, and there would be a trade-off between the penalty term and the cost term. But equivalently, we can write it as a constraint optimization problem. So instead of minimizing this, we can minimize G of W with the constraint that the regularizer is smaller than some mu. So we say that essentially, say, for example, L2 norm should be smaller than 10. And that would be equivalent of it with some specific choice of mu. So there is a correspondence between choice of mu and choice of lambda. And you can get a sense of, yeah, actually it's a good practice to think about it. Like if, say, lambda equal to 0, what do you think mu would be? Infinity, yes, so infinity. So if lambda is 0, we are not penalizing anything, which in the constraint formulation, it means that the regularizer can be anything, so it can be smaller than infinity, so that's fine. So what happens if lambda goes to infinity? What would be the corresponding mu? 0, yes. So if lambda is very, very large, going to infinity, basically we're saying that this term should dominate. And if that term dominates, it means that we only care about the size of the weights. And the minimizer for that is weights all equal to 0, which corresponds to here choice of mu would be, we can't allow any weights to be larger than 0. So that would be mu equal to 0. And then in between, of course, there would be a correspondence between them. But I guess the general idea is that one of them is growing, the other one is decreasing. Now we can formulate ridge regression and lasso in the form of this constraint optimization. So we minimize the cost function that we have, but we say that LP norm of the weights should be smaller than some mu. And when P is equal to 1, we get lasso. When P is equal to 2, we get ridge regression. So this is constraint formulation of it. But the reason I mentioned this is that I wanted to show this figure to you. So what is this figure? Let me try to explain it. And it might be small, hopefully you can see. So here, with W1 and W2 are the weights of our model. So this is the weight space visualization. So we have the set that xw minus t squared. So this is the cost function. Consider all the values of weights such that the cost function is smaller than some epsilon. So cost function, we want the fit to have error smaller than some epsilon. And epsilon is just a number. It's not necessarily very small value. It might be 5, for example. So this weight, so the set of all these weights define a set. How does that set look like? I mean, I've written it here. So it's ellipsoid. And I guess you can convince yourself this is a quadratic equation. So if you write it, expand it, it defines an ellipsoid in the weight space. So essentially it looks like this. This would be set like this. that at this point that I maybe use a different color. This is equal to point epsilon equal to 0. So we have a perfect fit, and then we gradually increase epsilon. So these are level sets of different values of the cost function. So if we find a point W here, we have the minimum training error. If we are at a point that is far, like here or here, we have a large training error. So this radius is your training error. So is it clear, that part? Okay, now in the constraint optimization viewpoint, we say that we want to find the minimum of this cost function. So we want to find the minimum epsilon that is possible. But we have a constraint, and the constraint is the weight should belong to a constraint set. So how does the constraint set look like? The constraint set look like, in the case of L2 norm, it would be, I think I have it here. So it would be the set of all W's where L2 norm of it is smaller than some mu, or general LP norm of it is smaller than. So what is the set of points which has L2 norm smaller than mu? Right, so it would be in set of points that some mu is exactly a circle essentially, or a ball essentially. This is defined, L2 norm defines, you remember L2 norm defines Euclidean distances. So I'm saying that I'm looking for the space of all weights that the Euclidean distance is to the origin is smaller than mu. So it defines essentially this kind of circle, which I guess I should erase. But that's red circle. Yes.
I don't understand what does the blue or purple circle and the dots and the vector.
The blue circles, you mean?
Yeah.
So that would be the set, this set. The points that all the weights that have xw minus t is smaller than some epsilon. So this is a quadratic equation in W's, right?
Okay.
So it has the minimum, and then I'm looking at its level sets at different levels of epsilon essentially. So the minimum would be at some point in this region. So say here is the minimum of it, which may or may not be actually 0. So maybe we don't have a solution for epsilon equal to 0, but it's a kind of defining quadratic set or quadratic curve. It has a minimum, and then I'm looking at different level sets of it. And as I get farther from this some point, its minimum, it is defining different level sets, but the shape of it is like a circle here. Or in general, it's an ellipsoid. So here I'm showing as just a symmetric ellipsoid, a circle. Okay, so we have, we want to find, okay, so that was L2 norm. What if I have a L1 norm for constraint sets? I guess you can try to convince yourself, maybe you need to think a little bit about it, that the shape looks like this diamond-like shape. So I think in 2 dimension, it is easy to see why it is the case, because this is essentially, we are saying W1 plus W2 is equal to some mu. So that would be the kind of the boundary of the region. And this essentially means that it's defining a line that at some value here, it becomes like mu. This is mu. And then in between, I'm decreasing epsilon, decreasing W1 by some value. If I want to maintain on the same surface or line, or curve, I have to increase the W2 with the same amount. So that's why defining a linear behavior instead of a curved behavior. So essentially, it looks like a diamond shape in high dimension. Okay, so we have two sets. One set was the set of feasible constraints. The other set is the set of level sets of error on the training set. We want to find the minimum cost. So we want to, so we want to be as close as possible to this minimum here. But we should find a weight that is exactly, that should be within this constraint set. So it should be in this region. Or for the L2 case, it should be within this region. So when that happened, the first time that these blue curves hit the orange region. So essentially, we increase the level sets until we hit that point. And where does the hit happens? For the L2 region, for the ridge regression, the hit happens at some point, like here. Maybe use a different color. It's happening at kind of that point. But for which doesn't have any special structure in general. But in the case that the domain is diamond-like shape, it is likely that the hit happens at one of these edges of that diamond shape. So it is less likely to hit kind of at this point, but it is more likely to hit at one of the edges. And this is clear in this figure, but also I should warn you that, okay, so if this is happening, what does it mean? If we hit at one of the edges, instead of just at a point like here, what does it mean about the weight that has been selected? Like, what is the property of this weight? In one of the coordinates, it's 0, right? So that's the answer. So some of the weights are going to be exactly 0. So if the hit happens at the edges, some of the weights are going to be exactly 0. That's the kind of intuition of why, if we use a set like L1 norm in this constraint formulation, we get weights that are going to be, some of them are going to be exactly 0. This is, of course, not a complete proof. I didn't prove it that's happening. Just I showed you that it looks like that. But people prove that in certain situations, lasso tends to find points that actually are going to be at the edges of that diamond-like shape. And as a result, the weights are going to be 0.
Sorry, does it guarantee it, or does it?
Both. Like there are empirical results. I guess that's easy to see, but there are theoretical results that showing that lasso tends to promote finding 0 weights under certain conditions. I guess, I mean, I don't want to, there's a large literature on lasso. Lasso, I think, was invented in 90s by Tip Shirani. But L1, the idea of L1 norm was there, I think, in 80s in the signal processing community to induce sparsity. But I guess in the form that I explained was in middle of 90s, maybe 94 or 96. And then, so there's a lot of theory developed around it. So there is a book by, I mean, if you want to go into it deeply, by Saurav van de Geer, it's called like a Statistics in High Dimension, which studies the theoretical property of lasso-like methods. And under certain conditions, then we can show that if there is a good sparse solution, sparse meaning that many of the weights can be zero, then lasso or methods similar to lasso tend to find. Right, so okay, so let's, so there's a question that, is it always desirable? That's actually, okay, so is it always desirable to have some coefficients of zero? This is actually a good point. Maybe I haven't really motivated why lasso is useful. In some situations it is. So I think lasso was promoted by applications in bioinformatics. And so I consider, I guess, a typical application of lasso is like this. Suppose you have gene expression data, which basically you kind of measure the expression of genes of some people. And then you want to find what genes or what gene expression leads to certain diseases or some certain health conditions. So these gene expression data usually has high dimensions. It would be order of maybe tens of thousands dimension. So the number of X, the dimension of X is say 10,000, for example. But the number of patients that you have, or not patients, but people that you have in your data set is usually small. You don't have millions of people with their genes, but you have maybe tens or hundreds of them at most. So the number of variables is actually many more than the number of genes. So that's one thing, the number of individuals, basically. That's one thing. The second thing is that you want to find a kind of relation between a person, what genes are leading to certain diseases, for example. And you want to have a minimum number of genes as possible. Like you want to identify these 5 genes are important. We don't want to find something that says that linear combination of 10,000 genes is important because you can't do much about it. You kind of want to find the causal structure here, at least get inspiration what causal structure might be there. I'm not talking about causal inference at this point now, but generally you want to find as minimum number of variables that affect certain disease. And a method like lasso would be very helpful in doing that because it promotes, it pushes weights that are basically not correlated with your output to zero as much as possible. So that's a kind of one of the motivations that lasso-like methods might be helpful. Okay, so I guess one question is whether how do we prefer lasso over ridge? So I guess if you want to have a sparse solution, lasso is the solution approach to go, ridge is not. In terms of if you don't care about that, it depends on the case. Like if you can describe your variables or your function with a few number of input dimensions, the lasso usually give a better solution. But if there is no such a structure, many of the variables contribute to the effect, then ridge might be better. But in practice, I guess you need to try both of them. So yes, I guess it's, the question is that as it makes one of the parameters equal to 0, does lasso generalize well? Depends. If there is a structure that the truth actually has a lot of irrelevant, if your data, like just gene expression, a lot of genes are not relevant, so you don't actually need to have any coefficient for them. In that case, it's generalized well. Is it not possible for the sets to intersect at an intercept for p equal to? I don't understand it. So there's a question that I feel for p equal to 1, it is not 100% that some of the weights are going to be 0. Yes, so it's not perfect. It depends on the costs, so it's more likely to make weights to be 0. That's true. Like, I mean, there's no guarantee that all of them would be 0 or more, even most of them, or even any of them. So in this figure, it happens. In many cases, empirically, it happens. for theoretical result, there are results showing that under these conditions it happens, but it is not always. Okay, so I guess I kind of answered when reach is preferred. Depends if we have sparse structure, lasso is preferred. If not, reach might be actually better. But in practice, in many cases, both of them perform relatively similar, so you have to try both of them. There is a kind of structure reason. So the idea is that I think okay, so maybe focusing on this thing. So regularize the function that quantifies how much we prefer one hypothesis versus another prior to seeing data. When regularizer is successful, the regularizer will be successful when our prior belief about what type of functions or models are better is actually correct. So this kind of hints which one might be better. If the truth is like that, the weights, L2 norm of weights are actually better model and generalize better, then in that case, reach performs better. If the truth is such that most of the weights should be 0, and we just want to find that, having a preference function that gives us pushes us to find solutions with 0 weights, that gives us a better solution. But that depends on the data actually. So you can't say without seeing data or without knowing how the data is generated. So in practice, if you're a machine learning engineer, data scientist, or anything, you want to see how it works, you have to try it, both methods with different hyperparameters on your validation set and see which one performs better. If you know it, data is like gene expression data, so you expect that from physiological point of view or biological point of view, it is better to have sparse. It makes sense to have sparse solutions, so lasso is preferred. Okay, so I explained this thing. Probabilistic interpretation of the squared error. I can't finish it in 4 minutes. So, yes. Oh, okay. I guess there's a delay. Okay, so perfect. I guess there's a delay. I don't know what's happening, but that's a point that I guess we should stop. Okay, we continue next time. So you don't need to send the question answers for this lecture yet because we haven't finished it. So next time I talk about the gives the probabilistic interpretation of this mean squared error. And then I start talking about classification. And that would be it. Okay, thank you.